Okay, so yesterday we are considering this autoregressive modeling. There's a small mistake I made which I want to correct. Actually, so let me redo it again because I don't remember exactly where it was. So let's just redo it. We had a model like this: x n plus summation a I x n minus I equal to say 1 to p. Say pth order model is say E n. Okay. In the case of autoregressive modeling, E n is a white sequence, maybe 0 bin white sequence, and it is a pth order model. It is an all pole model. If you take the Z transform, find out the transfer function, it is only poles. Alternatively, we have also shown that even if there is no such model, you want to just project, you want to just predict x n linearly from its past p values, x n minus 1 to x n minus p, and then x n, and let the prediction coefficients be minus a I, then the error will be what you see here on the left hand side, and that error, then also you have got a similar equation. So, both linear prediction and AR modeling give rise to same equation. Further, if it is linear prediction, we know E n is orthogonal, that is uncorrelated with the past p samples, because what we are doing is we are projecting x of n orthogonally on the space spanned by the past p samples x n minus 1 up to x n minus p, and the error then, because it is orthogonal projection, the error will be orthogonal to the total plane or total space spanned by x n minus 1 up to x n minus p. So, E n is orthogonal to the past p values. Similarly, in the case of AR modeling, I have seen yesterday that input E n, which is a white sequence, because the model is causal and all that, E n is orthogonal to all the past samples of x n, and therefore, the past p samples also. Since in the modeling problem where we will be estimating or finding out AIs, unknown AIs from the given data, we will be using only the orthogonality between E n and the past p samples. It does not matter whether you are solving a linear prediction problem or AR modeling problem, you will get the same set of equations and same solutions. Okay. Now, there we said that how to find out these equations. We know this orthogonality E of, this is what we did yesterday, and then I made a small mistake. So, I am redoing in this step. Say x star n minus k, that is equal to 0 for k equal to 1 to p. These are orthogonality. If you now substitute this left hand side for E n here and do the multiplication, then what you get out of this equation is, you can verify easily, for k equal to 1, say we start with k equal to 1, then go to k equal to 2, and then k equal to p progressively. For k equal to 1, you get firstly x n into x star n minus 1. So, that gives you r 1. I am putting this lag in the subscript, then r 0, then what we have next term is x n minus 1 times x star n minus 2 expected value. This is equal to what? This is equal to the correlation for lag what? N minus 1 minus within bracket n minus 2. Okay. I think, so what is the first one? Let me maybe just take the first one. First one is, if you put this expression for E n here, take the first term x n. So, x n x star n minus 1, if you take E of that, you obviously get R 1. Next term is E of, I am not taking the coefficients, they will be handled separately. This let me do elaborately, because by skipping some steps I was making mistake, or maybe it was resulting in confusion. Next term is n minus 2. So, what is this? This index n minus 2 minus within bracket n minus 1. So, correlation at lag minus 1. So, this is r minus 1. Yesterday I put a star also along with it. Instead of writing as r minus 1, I made it r minus 1 star, which was wrong. Okay. So, let me erase this part. Very well understand what I am going to do. R 1, R 0, r minus 1 dot dot dot. Last one will be what? n minus p, okay, x n minus p, x star n minus 1. So, R within bracket minus p minus 1. Form a matrix 1 A1 dot 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 AP, this is equal to 0 dot 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 0. Again I say it is not Ax equal to 0 kind of equation, because you have got a 1 here which is a known quantity. So, 1 times R1 that has to be taken out to the right hand side. If you do the first row times this column, this multiplication, you get one equation out of which R1 into 1 is a known quantity that can be taken to the right hand side. Same for other rows, you get a set of linear equations, solve them, and by solving whatever values you get, you plug in this model, you get a transfer function. So, you know the mod square of the transfer function times the variance, some constant will be the power spectral density. So, basically you have to solve these equations. What are the other equations here? Now, put k equal to 2. If you put k equal to 2, what do you get? Absolutely similar steps. If you put k equal to 2, you have here R2, then R1, R0, R minus 1 dot dot dot, or this p minus 2, so on and so forth. When you have got k equal to p, then you have got R0 here, and what you have here k equal to p means Rp dot dot dot, this kind of thing. Okay. Now, I also now put k equal to 0 here, suppose. Why leave out k equal to 0 case? If I put k equal to 0, what you get here is just n. There is a k equal to 0 case. What is this? In the case of whether it is linear prediction or air modeling, in each case, in the case of linear prediction, say, what is x n? X n is x cap n plus E n. What is x cap n? It is the orthogonal projection or rather prediction of x n from the past p values. This is x cap n is nothing but a linear combination of x n minus 1 up to x n minus p, and the error is E n, the summation of the two is x n. If you put that back here, E n is orthogonal to x cap n, because x cap n consists of the past p samples x n minus 1 up to x n minus p, E n is orthogonal to them. So, E n times that with a conjugate on this x cap n, that becomes 0 because they are orthogonal, therefore uncorrelated. So, what you are left with is E of E n into E star n, that is E of mod E n square, which is the variance of E n. Alternatively, in the case of air modeling problem, we know that, I mean, you view x cap n as what? X cap n as the prediction or orthogonal projection of x n, not on the space spanned by the just past p samples, but by all past samples. That is x cap n, and the error is E n. E n is orthogonal to this x cap n by the same logic, and you put them back here. You once again get E of mod E n square, which is a variance. Okay. So, that means if you put r equal to 0 here, in the equation what you get, you substitute the left hand side for E n as before, you will see you will get this equation. And this is equal to the variance we denote as, this is same as E n now, and this is not 0. This is called forward prediction, because from the past samples we are predicting future. So, it is a forward direction prediction. So, that is why it is a forward prediction error variance. Sigma square is usually used for variance. So, sigma f square forward, f for forward. We also put a subscript p to denote that it is a pth order linear prediction or pth order modeling problems. Mind you, this is unknown, because input E n or the prediction error E n is not known to us, and therefore, this is unknown, but still we put like this. So, how to solve the equation? First, forget about the first row, just take the second row to the pth row, okay, to the last row, solve them, get A1 to AP, Now put them back in this vector. Now take the first row times this column, whatever you get, that is sigma p f square. That is the input variance. So what is the output perspective density? Input variance times, because input is white, so input variance times mod square of the transfer function. Transfer function we know, because you know what is Hz, that is 1 by 1 plus A1 Z inverse plus A2 Z inverse 2 plus dot 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 plus AP Z inverse P. So all the A1 to AP are now known because you have solved these equations. So you know the transfer function, you know the mod square of that times this variance, that will be the perspective density. That is how you have to go about it. This equation is a famous equation in the context of linear prediction or air modeling, and this is called Yule-Walker equation. As far as perspective estimation is concerned, you just have to solve it, that is all. Once you know A1 to AP, okay, you are through. Of course, you need the values for R0, R1 and all that, but in the previous case only, while discussing periodogram, I told you, given a data record for Xn of sufficiently large data record, you can do sample estimate, you know, I mean just sample estimate, I have given the formula also, sample estimate for R0, R1, R minus 1 and all that. So, once you have a sufficiently long data record for Xn, just by sample estimate technique, okay, sample and average technique, say, you can find out the correlation values. Okay. Now, this Yule-Walker equation is fine, but you know these equations lead to something else. There are firstly, there will be some very fast algorithm to solve this, and that algorithm leads to a structure, a kind of filter called lattice filter, which has some interesting properties and very useful in linear prediction context. So, I will see if I can give some introduction to lattice. So, this matrix I call R within bracket P. You see, this is called a Toeplitz matrix. In a Toeplitz matrix, if you know one diagonal entry, that entire diagonal is repeating, you see. Similarly, R minus 1, it repeats along these, R1 repeats along these, okay. R2 repeats like that, and R minus 1, R1, these elements are actually conjugate of each other, you know, R minus 1, R1 star, or R minus 1 star is R1, we know, R minus 2 star. So, it is actually a conjugate symmetric matrix. Any ijth element and jith element, they are conjugate of each other, and also Toeplitz. Any conjugate symmetric matrix in short called Hermitian matrix. So, it is Toeplitz and Hermitian both. So, if you know one row, it is enough, you can construct the entire matrix. First, the diagonal elements will be same, so you can construct, you can slide along the diagonals or subdiagonals and construct one half, the upper triangle, and then using the conjugate symmetry, if this is R minus 1, you know this should be R1, so on and so forth, and you can construct the lower half also. This vector I call, say, AP vector, sorry. This P denotes here, that is a pth order modeling problem or pth order linear prediction problem that is being considered. Okay. Remember one thing, this is RP, and if I partition this matrix like this, take out first row and first column, what you get here is RP minus 1. That is, instead of RP filter RP minus 1, whatever I would have got, like here I went up to R minus P, for P minus 1, for RP minus 1 I would have gone up to R minus within bracket P minus 1, that is what I am getting here. So, this part is RP minus 1 and then one row and one column. Alternatively, you can also take this matrix like this, where this part is RP minus 1. Okay. So, we write like this, one row, one column, leave it, this is RP minus 1, alternatively this is called matrix partitioning, sorry. Okay, this we know, keep this result as somewhere. Now, along with the forward prediction, there is another problem that is also tackled simultaneously. that is called problem of backward prediction. Backward prediction means if you want to predict x, the past sample, say x n minus p, from its p future values. What are the p future values? X of n minus 1 dot 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 up to x of n minus p plus 1. So, from the p future values, if you want to predict x n minus p as a linear combination and let the coefficients be minus b I minus b I, you write like this, sorry, p plus I equal to 1 to p. So, this is the error. This error you call previous error earlier, so long I denoted E n, that will now be written previously whatever was E n, that will now be written as E f, because that was related to forward prediction, E f pth order n. So, whatever you did for E n, I mean whenever you had E n earlier, wherever you replace that E n by this E p f n, pth order forward prediction error. Okay. Using that terminology, I mean analogously, this will be pth order backward prediction error, E p b n. It is n and not n minus p, because this is the convention. We look at the latest sample in this left hand side. Latest sample is when I equal to p, you put p here, you still get x n. That is x n minus p is predicted from p future values. So, p future values are x n minus p plus 1, x n minus p plus 2, x n minus p plus 3 dot 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 up to x n. Since n is the current index, the convention is to put n here. Okay. And these are the coefficients. So, what you get actually, minus minus become plus. So, you get obviously, this is orthogonal to what? Orthogonal to the space spanned by those p future elements. Earlier it was p past elements, now p future elements. So, E p b n is orthogonal to x n, x n minus 1, x n minus 2 dot 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 up to x n minus p plus 1. So, those p future values starting, I mean for this sample x n minus p, that is if you go p steps in future, those p future values samples, they are orthogonal to E p b n. That means, if I now use that orthogonality in this way, that okay, multiply the left hand side by say, that means if I put it like this, E of into x star this will be equal to 0. You start at I equal to p, go backward, p minus 1 dot 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 up to 1. If I do that, you can see one thing. For suppose put I equal to p, if you put I equal to p, it is x star n. Okay. If you put x star n, what do you have? If you put x star n and this E p b n is replaced by the left hand side, in the left hand side you start at the in this summation for I equal to p, take I equal to p case, then p minus 1, p minus 2 dot dot I equal to 1, then n minus p. This is how you go about. Okay. That is, I repeat my steps. E p b n is to be replaced by the left hand side here of this equation, and then you have to do term wise multiplication, but we start first with whom? In the left hand side, you have a term involving x n minus p with that. Then next time I consider x n minus, sorry, first we consider the term that is x n, that is when you put I equal to p, p n minus p cancels, x n. First we start with x n, then x n minus 1, then x n minus 2 dot dot dot, and then finally x n minus p. Okay, this is how I order this thing. Actually, what we are doing, we are just putting replacing EPBN by the expression and doing the term-wise multiplication. Only we are doing it in a particular order, and that order is described. So, first I equal to p, and once you have I equal to p case, this is x star n, and this is x star n, and then you are starting with x n here. So, what you are getting is, I need space here. So, maybe what do I rewrite this here and generate some space. The same equation I am rewriting, and then I will erase this bottom one, some space will be generated, I will use it. Okay. And what was EPBN? EPBN was, just for our reference, what was EPBN? X n minus p plus b I x n minus p plus I was 1 to p, that was your EPBN. Okay. Now, this EPBN is replaced by this left hand side in this equation, and we do term-wise multiplication in the particular order. So, first I equal to p. I equal to p means what do you have? I equal to p means x star n, and in that summation you start at x n. So, essentially product will give rise to R 0, then x n minus 1 into x star n, product will give rise to R minus 1, then x n minus 2. You understand? First it was x n into x star n, it gave you R 0, then x n minus 1 into x star n, it gave you R minus 1, then R minus 2 dot dot dot, and finally x n minus p into x star n, that will give you R minus p star. Okay. Then what you have? So, I repeat again what I did. I took p equal to 1, I equal to p, and that is orthogonal, EPBN is orthogonal to that. So, EPBN is this, and I do term-wise multiplication, x n into x star n, that will give rise to R 0, x n minus 1 to x star n, that will give rise to R minus 1 dot dot dot. Okay. And finally, x n minus p into x star n, that will give rise to this. Then p I equal to p minus 1. If you do that, you will get, I am sure, R 1 here, because x n into x star n minus 1, that is R 1, then R 0, then R minus 1 dot dot dot, R minus within bracket p minus 1 star, so on and so forth. When I equal to 1, n minus p plus 1, n minus p plus 1, x star n minus p plus 1. So, x n into that, so it will be R p minus 1 dot 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 dot, R 0, and then n minus p plus 1 star, still R minus 1. You will get that times B p we are writing it like this. Earlier I just wrote A p, A1, A2, A3, but I am now putting a subscript p just to indicate that these are related to pth order backward prediction. Similarly, previously if I had AI, that will be now A pi. Okay. Earlier I did not want this confusion, so I did not bring the subscript. sorry, all these are zeros. Again you can solve them. It is not again A x equal to 0 equation, because there is a 1 here. So, 1 for the first equation 1 times r minus p star, that is a now known quantity, you can take it to the right hand side, same for other rows, and you solve, you get these values, and so you know what is the backward prediction error, I mean these coefficients and all that. Okay. Now, look at this matrix, and now I want to do the case for, I want to also include a particular case. What is that case? I went from say I equal to 0. If I take I equal to 0, then what happens? If I take I equal to 0, that is this goes, and this is not 0 surely, because it is x n minus p. Okay. And what is x n minus p? This, by now you should be able to do this. What is x n minus p? X n minus p has got two parts. One is x n minus p, you can write separately here. As its prediction, which is a linear combination of the p future elements and the corresponding error E p b n. This x cap n minus p is what? Its prediction. There is a linear combination of the p future values, that is orthogonal to E p b n. So, that product will go as 0. So, what you get is not nothing but E of mod E p b n square, that is the variance of the backward prediction error for pth order. Okay. So, that means exactly similar step as I did for the forward prediction case. This is nothing but sigma p, but this time not f but b for backward square. And so, here you have this quantity sigma p b square. This is unknown. So, first you solve for the b values, the coefficients. Once you know them, the last row times this column will give you this unknown quantity. Okay, now, look at this matrix again. You can see that this is again the same R, okay, same R matrix. This is the beauty, same R times a backward prediction error vector of this type, backward prediction coefficient vector of this type will give you an equation of this kind, where this top ones are 0 and last one is an unknown but positive quantity. Previous case R into, there was another vector where starting one was 1, 1, AP1, AP2 dot dot APP. Then on the right hand side first term was an unknown positive quantity, all the terms were 0. These two equations are to be solved simultaneously, and there I will be cleverly using this partitioning of RP, and there an order recursive solution comes which gives us to a lattice filter. We can just easily derive it now. So, I do not have to bother about the structure of R now, or you remember. It is an order recursive solution. So, suppose I know the pth order solution, that is suppose R p into 1 A p 1 dot 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 A p p, this equation is known, sigma p f square 0 dot 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 0. This is solved. So, I know these unknown coefficients, I know sigma p f square, and also R p times this also is known. Okay. What will be the corresponding solution for p plus 1th order? So, we will develop an order recursive solution. So, you can see if I have R p plus 1, the equation that I am trying to solve here is this. See, length has gone up by 1. Earlier I had up to p, now it is p plus 1, and this will be again that unknown quantity sigma p plus 1 f square 0 dot 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 0. Suppose I want to solve this. You can see one thing, I can, if I propose a solution like this, that look, but before that I know this matrix partitioning. So, if it is instead of p, if I make it p plus 1, then this becomes just p, this p is replaced by p plus 1. Now, suppose I first propose a solution like this, that can the solution be of this type 1 a p plus 1 1 dot 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 a p plus 1 p, this is the unknown vector in this equation. Can it be a linear combination of the two vectors of the previous order, that is 1 a p 1 dot 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 a p p, this is the a vector for the previous order pth order. We are assuming that we have already solved this for the pth order. So, we know this coefficient. So, take them and put a 0 and some constant maybe k p you can call times again a 0 here and then this previous solution for backward prediction b p p dot 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 b p 1 1. My point is, can I am just proposing and let us verify that it is possible by a particular choice of k p. Can we write the p plus 1th order forward predictor, if we call it forward predictor, coefficients are called predictor coefficients, so forward predictor as a linear combination of the pth order forward predictor and a 0 and a pth order backward predictor and a 0 on top. Can we do like this? Suppose we do. What is happening? You have to put then this on the left hand side. Can it solve can it satisfy an equation like this, where on the right hand side unknown is a positive quantity, but unknown quantity and all the terms are 0. Now, you see, first if you have r p plus 1 times this vector, you do this first partition of the matrix r p and then column column. So, r p plus 1 into this vector 1 a p 1 up to a p p and then 0. What does it amount to actually? It amounts to nothing but r p times this first part and 0 times whatever be the last element of each row here, and 0 takes care, 0 makes everything 0. So, actually if you put that back here, what you get? I hope you can remember this part, because there is a shortage of space. If you put this back here, what do you get? Using the first partition of the matrix, r p times maybe you can call it a p. What is a p? This part. This part you are calling a p, this part say you are calling say b p. So, r p times a p plus whatever be the single element left in this column, that times 0. So, 0 takes care of it. So, this r p times a p, and we already have solved this equation. I know what is r p times a p, that is sigma p f square and then all zeros, and then there is a last row, this last row times this. So, that is some unknown quantity, that is some not unknown, this is some known quantity, you can call it say alpha, some alpha p. What is alpha p? Last row of r p plus 1 times this vector a p and 0, that will be here, plus k p times, this time I will use the second partition. If you use the second partition, what do you have? First row times this vector 0 and then b p, this vector 0 and b p. What will that be? That will be some quantity you have to calculate, that is b p. All the values are known here. You can call it beta p But what happens after that? First entry of each row here times the 0. So, forget about the first entry because the 0 will take care of it. So, basically you get RP times BP vector. Okay. And you see what is RPAP? RPAP you have seen because we have already solved that equation. What is RPAP? That is nothing but, what is RPAP? Sigma P f square and then 0 0 up to 0. And what is RPBP? RPBP is sigma P B square then 0 0 0. Okay. So, these two should be equal to this right hand side. Right hand side is what? Sigma P plus 1 f square then 0 0 0. Sigma P plus 1 f square is an unknown but positive quantity. Now, you see one thing, there are two vectors on the left hand side here and both the vectors have some non-zero quantities on the top and the bottom, but in the middle there are zeros. So, at least I am able to get all the zeros here. 0 plus Kp times 0 is 0. So, the zeros are matching. In the last row, alpha p plus Kp times sigma p b square, that also must be equal to 0. So, solving that I get a Kp. So, that means what is Kp? For the last row, I know what should be Kp. So, I can choose a Kp like this, that alpha p plus Kp times sigma p b square equal to 0. So, that the last equation is satisfied, which gives rise to what? Put that Kp here, back here. So, sigma p f square plus that Kp times beta p, that will be now this unknown quantity sigma p plus 1 f square. So, that means just we have to find out Kp, and using the Kp you have to just linearly combine the two solutions AP and the 0 and 0 and BP. So, so that means what is the solution then for this equation? What is the solution? Let me erase everything now. What is the solution? AP plus 1, which by definition is of this form, AP plus 1, 1 up to AP plus 1, P plus 1, that is AP 0 plus Kp 0 Bp. You see one thing, the top coefficients, even if you linearly combine the right hand, if you carry out the right hand side equation, I mean summation, you still get 1 at the top, because what is the topmost term in AP? That is 1, 1 plus Kp into 0. So, you will get back the 1. So, that is satisfied, please note that. So, this is one solution. We already know what is Kp. Kp came out to be some minus alpha p by sigma p f square. Similarly, we can find out Bp plus 1. Now, it will be very simple, because it will be very analogous to what we did so far. We propose Bp plus 1 of this form, 0 Bp plus some coefficient Kp prime times AP 0. Question is it possible? Is it viable? What is the equation we have to solve? We have to solve this equation, Rp plus 1 Bp plus 1 is equal to something of this form, 0 0 0 and then unknown positive quantity sigma p plus 1 b square. If you substitute Bp plus 1 here by this right hand side expression, what you get by similar argument, what you get here is this. You will be using this matrix partitioning as before. So, in the first terms Rp plus 1 times this 0 and Bp, this vector, I will be using the second partitioning, and obviously what I get is this, I will get an unknown quantity on the top, sorry, unknown quantity, say beta p on top, okay, the first row of this matrix times this vector 0 and BP, that will give some beta p, and then first element of each of these rows, that will get multiplied by 0 here. So, forget that. So, R p times B p, and what is R p times B p? R p times B p is, we know, 0 0 dot dot 0 and then sigma p b square, and k p prime times, you put that vector again, this time use the first partition, R p times A p only, the other element, the last column elements get multiplied by 0. So, forget that. R p A p is what again? From the previous solution we know, R p A p is sigma p f square, then 0 0 0, and the last term is some alpha p. This must be of this form 0 dot dot 0 sigma p plus 1 b square. So, all the zeros are already made, 0 plus k p prime times 0 is 0, except for the first term beta p plus k p prime times sigma p f square, that must be equal to 0. So, I can find out what is k p prime here. K p prime should be equal to this k p prime is equal to I think this was previously, it was wrong, it was okay. In fact, so you put that back here, okay, and you now get what is sigma p plus 1 b square from the last equation. In fact, I am not, there is no time to go into all those details, but k p and k p prime can be shown to be same, you know, in this equation can be same. In fact, one is the conjugate of the other, to be frank. K p prime is the conjugate of k p and vice versa. Sigma p b square, sigma p f square, they are same, that comes from stationarity. These results I am not showing here. Okay. So, from past solution you can find out the future solution. Only thing is how to start the recursion. Okay. Now, we erase this. We know the solution, we know what is k p and k p prime, the solutions are known to us. Okay. And how to start the recursion? Because I assume that A p is known, P p is known, and then found out A p plus 1, B p plus 1. A 0 is obviously 1, B 0 is 1, because that is the topmost coefficient. So, you can find out what is, sorry, A 0 A 0 vector is actually a vector with having element 1, B 0 vector is 1, because the topmost element is 1. So, when you consider the 0th order, you are left with only that. So, 1 1. This is how you start. One thing you note, and that is important, is that what was EPFN? That was 1 times okay. Now, that means this is what AP transpose, AP vector transpose. Okay. So, what is EP plus 1 Fn? That will be by the same logic times what xn dot 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 up to one more term minus 1. Okay. Now, we know what is AP plus 1. If we substitute AP plus 1 by this thing, AP 0 and then KP into 0, KP into the vector with 0 BP, put that back here, what you get? If you put that back here, you see these are simple steps and there is no point in wasting time on that. First term is AP 0. So, forget out the last entry of this vector. So, you get AP transpose xn. Okay, AP transpose xn, last entry of this vector xn minus p minus 1, that is not, that is to be discarded here because that gets multiplied by 0. So, what you get is AP transpose xn, and what is AP transpose xn? That is again EPFN, and Kp, Kp is what? Beta p minus this, so Kp, Kp times, now what is this? You have 0 Bp, this vector in a transpose form times this matrix. So, 0 into first entry xn, forget that. Okay. So, you start at n minus 1. So, Bp transpose which vector? You get a term like Bp transpose x n minus 1 dot 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 up to x n minus p minus 1, that I can write as n minus 1 minus p. Suppose n minus 1 is n prime. So, it is x n prime dot 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 up to x n prime minus p. So, that will be again what? E p b at n prime is n minus 1. And what is the AP transpose xn? We have already seen, this is from previously we have seen, this is EPFN. Okay. Similarly, so EP plus 1, this is very important equation, EP plus 1 Fn is EPFN plus Kp times EPB n minus 1. Then the question is, what is EP plus 1 Bn? That is again Bp plus 1 transpose this vector, Bp plus 1 transpose this vector xn up to xn minus p minus 1 up to xn minus p minus 1. Now, you replace Bp plus 1 by what you have on the right hand side. So, in the first case you have got a vector that has 0 and Bp transpose, 0 cancels the first term. So, what you get is what we have seen already, first is EPB n minus 1 and second term, that is Kp prime, another vector is AP0 transpose. We have already done it in the previous case, AP0, AP and 0 transpose. So, the 0 is the last term, forget the last term, AP transpose a vector that starts at xn and goes up to xn minus p. So, AP transpose that vector is once again EPFN. Okay. So, if you just consider these equations, these two equations now, forget the entire thing, you get a beautiful structure. What is the structure? If you have this is Kp multiplied, this is Kp prime. These two are conjugate of each other. We are not, I am not proving it. It can be proved easily. You can try. It is given in books. So, this is order recursive. And the same structure I can use again. So, I can just cascade this structure after this. I mean, just connect it the same structure after this. just coefficients will be Kp plus 1 and Kp plus 1 prime. So, from Ep plus 1 Fn and Ep plus 1 Bn, I can generate the same errors for P plus 2th order and then P plus 3rd order, so and so. So, this is order recursive. Very first stage, you know that for 0th order case, for 0th order case, forward and backward prediction errors are same and there is xn. Okay. So, xn is, that is E 0 Fn, there is 0th order is same as E 0 Bn is same as xn. So, you can generate this first order things the same way. This K1, this K1 prime. This is called a lattice filter. This is one of the most celebrated things in statistical signal processing. This is used for air modeling and particularly used in speech context, because I mean our speech generation mechanism in our vocal code has been modeled as some kind of modeled by an air model which is driven by some white sequence. Only thing, the air model parameters get changed from time to time and you produce various sounds. Okay. So, this air model is exactly predicted, modeled by this. I mean, from this you can find out the model parameters and all that. So, that is why it is very useful for speech processing. You can, I will not go into that because this is not a course on speech processing. Okay. So, it just shows how modeling, air modeling problem is related with linear prediction and lattice filters and all that. Only thing that I have so far not shown and I should show in maybe 5 or 10 minutes in the next class is that when you solve the Yule-Walker equations, you get a set of coefficients A1, AP1, AP2, dot dot APP. You put them back in the transfer function for a z. So, you get a transfer function something like this, a z dash, this is that air model transfer function. Now, this is the all pole transfer function. The poles for this model to be viable, that is stable and causal, the poles must lie within unit circle, and we will show that by solving Yule-Walker equations. Okay, whatever you get, that is those coefficients indeed ensure that the roots here, that is the poles here, that is the coefficients AP1, AP2, APP, whatever you obtain, this is APP, they are such that the corresponding poles are indeed within unit circle. Such a polynomial is called minimum phase if its roots lie within unit circle. This I will prove in the next class. Okay. And then I will go for another application of the stochastic process theory, which is the general mean square estimation and Wiener filter and adaptive filter, and some examples of that, and that will take us to the end of this course. Thank you very much. Okay. Last class we have been discussing this autoregressive modeling, and then we gave you the equations whose solution give rise to the air parameters. Also, we derived what is called that linear prediction lattice. Okay. Just few things, a little more things about this air modeling will be considered today. First, that is, suppose we have got a white process UN. I called it EN last time, but maybe I change it to EN. Say EN okay. This is xn. We are considering either air modeling or linear prediction problem. In any case, we have got this equation. Say a pth order problem into En. If it is a linear prediction problem, En is orthogonal to the past p samples, that is x n minus 1, x n minus 2 up to x n minus p. If it is an air modeling problem, En is a white sequence and is orthogonal to all the past of x. Okay. In the case of linear prediction, En is not a white sequence. En is orthogonal only to x n minus 1 up to x n minus p. Okay. In general, it is not an orthogonal sequence. In any case, En will be a sequence. So, you can model this even in the case of linear prediction. You can model this by a filter like this, that okay, there is a linear prediction error sequence called En, okay, may not be white, and white in the case of air process. It is passing through a model Az. What is Az? That is the transfer function of this AR system and gives rise to Xn. What is Az? Az is Xz by Ez. If you take Z transform left hand side and right hand side, obviously you get that all pole transfer function, and that is your Az. And here I got twice Rw. Remember, this is the gradient expression. I will use it in the adaptive filter. This gradient should be 0 when I have got the minima. That obviously will give rise to the same Wiener filter. You can see W cap equal to R inverse P. Okay, this is the optimal filter. In practice, if you know R and P, fine, you can calculate this R inverse P, but problem is R and P are not always known. R and P are not always known. In that case, you have to supply information, this information externally. Okay. What do you do? This actually gives rise to the interesting case of adaptive filter. When R and P are not known, or when the input statistics or the joint statistics between Dn and Xn, they change from time to time, you cannot have one filter designed once for all. So, what you should have? You should try to have some adaptive mechanism by which your filter learns from the data that is coming in and tries to adjust itself by some iterative method, so that finally it converges on what should be the corresponding Wiener filter for a given R and given P. Then again, after a while, if R and P changes, then again that adaptive mechanism will be used. It will further read from the data and readjusts itself, so that you get a new R and new P, and you get another corresponding Wiener filter. So, there will be continuous adaptation mechanism. If input R and P changes, it will track, and it will have an iterative self adjustment procedure, and it will finally converge. Every time that iterative procedure should converge at the corresponding Wiener filter. There are plenty of adaptive filter algorithms, but most celebrated is that least mean square algorithm, which we will be just considering in the next class, and I will just give one or two applications, like channel equalization in communication and all that. Okay, that will end this course. Thank you very much.